もどんなに祈り続けてても思い通り何もいかなくってそんな日もあるからどうかさ許してくれよ上向いて笑い合おうよ透き通る青色のパステありがとうごめんね教えて未来彩る明日も明後日もそこにいるよ
Hello, we are so glad to see you on campus. There are a few things that we need to let you know before we start the lecture. First, please make sure that you have your mask on all the time when you are in the classroom. Also, please make sure that when you are having a seat, try to keep a social distance with others if possible. If you feel sick, no matter it's physically or mentally, please stay at home. We do provide various online resources to keep you learning. Now, please sit back, relax, and enjoy the lecture. Today we are going to continue our series on cloud storage, and we have been talking about Google File System since the last lecture, and today we are going to talk about continue our discussion on Google File System, but we are also going to talk about Windows Azure, and that's why we played a song called Azure before the lecture. Well, it's the only song that I feel modern enough regarding the topic of Azure. So that's why I play that song. But before we start, I know it has been a weekend and probably you guys spend most of the time working on the project, so you probably have no idea where we were in the last lecture. But actually the last lecture is very important in a way that we try to tell you more detail about the design of modern file system running on top of the network, and we have been talking about the file system can be on the the network of your local area. For example, you can use network file system. However, if you want to use that kind of network file system in a larger scale, for example, in a data center setup, then the NFS is very inefficient in a way that, as we can tell, there are so many round trips that we have to deal with. So then it turns out that a Google file system try to address this drawbacks in a certain way that, first of all, again, right, there's no absolute, there's no Bible in terms of a file system design. It's all depending on where you are going to use that file system for. And if you look at the data center workload, it's typically based on inexpensive disks that often fail. And it's dealing with large files in contrast to small files. It's primarily reading strings of data instead of reading random data, right? And it's sequential writes getting to the end of existing file rather than random writes. And but one thing that's unique in data centers is that a single file might have multiple readers, multiple clients accessing it. So you must have good concurrency support.
And finally, because it's the era of big data, so we want to get data in with larger bandwidth to maximize the throughput of processing. So the whole thing together brings up the idea of data center, well, the Google file system. And this 6 characteristic that we mentioned is actually coming from this 3 main line research that, services that Google tried to power for their data centers. So it turns out this is what they propose. They try to maintain the same interface, and they try to organize files into large chunks. And they propose a flat structure. They propose a distributed architecture that's composed of master chunk servers and clients. And in the last lecture, we talked about large chunks, and today we are going to continue talking about the rest. And the reason, well, so we start with the large chunks, and the reason why they pick large chunks is because, as many of you already learned, disks, they will give you the best bandwidth in large chunks. So first of all, right, it will fit the design target of bandwidth. And then large chunks also facilitate the write behavior because you allocate a large chunk. So whenever you want to write, it's already there. And for reading streams of data, large chunks would help, right? And you have large files, so it makes sense to have large chunks. So today we are going to continue our discussion on Google File System. I bet we will have chance to talk the majority about the Windows Azure, and we probably don't have time to talk about Facebook, but we will see. So the second thing that I want to talk about in Google File System design is the flat structure. So we have been well educated in a way that in Unix or almost every kind of file system that we are interacting, or every kind of operating system that we are interacting, the directory structure is mostly hierarchy. And whenever you want to get a file within the directory, you have to go through the hierarchy. You have to extend the content of the hierarchy. So we accept that all the time. And in fact, we love that abstraction because they make the user easier to find the stuff they want, easier to organize the stuff. So Google maintained that abstraction in a certain way that from the application perspective, when you try to open a file, it's all, you can still specify the hierarchical directory. However, it doesn't really implement this directories. Instead, directories are illusions. What do you mean by illusion? So it's just like so unlike many traditional file systems, does not have the per directory data structure. And it doesn't support alias for the same file or directory. And it logically represents its namespace as a lookup table, mapping full path name to metadata. So what does that mean is that, okay, so directory is now just part of the file name. And you can consider directory names or the path just as the prefix of the file. So the purpose of that is, first of all, you can still maintain the same convention as the conventional file system and make you feel easier to organize your files still. However, in terms of the real operation, it's just a single mapping that it's a hash table like or mapping table like structure that you just give me the full path and I would just give you the real location. So now my question is, why this design?
All right, let's wrap up in 10 seconds. 5, 4, 3, 2, 1. Time is up. Okay. Ta-da! Okay, I love this graph because it means that we need discussion. So why don't you go ahead, discuss with your friend for maybe another minute or two. Go. Oh. All right, let's wrap up in 10 seconds. 5, 4, 3, 2, 1. Time is up. Okay, look at what you guys think. Ha. So C is getting more. B has 5, D has 15. So most of you agree. Well, it is C, D, E, right? Something like 3 and 4. Okay, what do you guys think? For people online, let me ask people online first. Well, some of you suggest that, well, if the group is too small, no one is discussing. So the TA were in group 2. So can someone in group 2 online tell us what do you guys think? Hello. So I have Abraham, I have Ashwaya, I have Pelagie, I have Christina, I have Amren, I have Marcus, I have Rohit, I have Sharens, I have Sari Devi, I have Tianze, I have Vinit, I have Zhen Quan, I have Ji Yang, I have Ji Yuan. Anyone here would like to say anything? Come on, you guys must have to say anything. I cannot have you idle online. Hello, somebody there? If nobody speaks, then this group of people, you won't get attendance for today.
I'm
Okay.
sorry.
Okay.
Actually,
that's really effective.
A member in our group say D is correct, but it seems like everybody is confused.
Confused. Okay, but so doesn't matter, right? So the thing is that I want to hear what you guys think so that I can clarify those. So that's the purpose of discussion. So tell me what you guys think and why you are confused. That's what I really want to hear. I don't want you to give me the right answer. You only need to give me that during your exam. But now is the time to tell me what you guys think. So what do you guys think, and what are you guys confusing?
We just don't know the difference between flat design and hierarchical design. What's the difference?
So, okay, so what's the difference between the flat design and hierarchical design? So the flat design, what it says is that, right, whenever, I think I did mention in the very beginning, right, the flat design means that when you want to look up a file, we treat the path as part of the file name. And when you want to find a file, it's essentially a lookup table. Did you remember that?
Yes.
You guys remember that? Right? It's here, right? So directories are illusion, right? So it's a lookup table mapping the full path names, including your file name, to metadata. What's a design? Do you remember? Do you remember that we were asking you how many times you have to go through the disk to retrieve a file, right? Remember that? Yeah. On the microphone.
Yes.
Okay, here, good, right? So the thing is, right, that's hierarchical design. Now, can you feel the difference?
Yeah. Yes. I remember the I know.
Okay, so
Yeah.
yeah, so the hierarchical design means that you have to go through each layer in the file system structure to finally reach the file you want, right? But the flat design means you can directly find a file, right? So thinking about a company, what's the difference between hierarchical and flat structure? So for example, startup companies, they typically are flat structure that everyone is reporting to the founder or say the CEO or CTO, right? But if you are in a big company, right, you have to report in a layer like, okay, if I'm an employee, I'm an engineer, I have to report to my manager has to go through the VP, and the VP has to go through the president, and the president has to report to CTO, CEO, whoever your upper one is, right? So if you want something to happen, there are so many steps you have to go through, right? But for the flat structure, once you have something, tell your boss is all set, right? But in a flat structure, it's not about that, right? So that's flat structure and hierarchical structure. So based on that, what do you guys think about this statement now? Online. All right, that's okay. But thanks a lot for you stepping out to save your group. And you did a good job. So, okay, so here's the thing, right? So people here show that the in-person experience is better than online experience. So how do you guys think about the first statement now? Given we have clarified the difference between structure, the flat structure and the hierarchical. Well, what do you feel the first? Any help? Any difference? There's no difference, right? Because if the disk failed, it still failed, right? How about the second one? Any difference? Not really, right? Because it doesn't matter, right? How about the third one? It could be faster. Really? In what way? So here's the thing, right? Okay. It could be faster, but it's faster because of what's improved. The lookup is improved. So The other thing is that does the improvement apply to any kind of file? Every file needs lookup. Doesn't matter if it's read or write. Doesn't matter if it's random or a string. You agree? So you cannot conclude saying that is contributing to this one. You agree? Do you agree? It's not contributing to this one. It's actually help everyone. So it's not aiming at this. Okay. So another lesson that you learn is that a lot of people, when they try to interview for a position, for a job, for a company, they try to, or even for you guys, when you try to answer things on your midterm or final, you try to throw everything you know. But sometimes, if you are not specific, it's actually hurting you because it will reveal that you don't actually know. So here is what I'm saying is that, okay, sometimes you think it's relevant, but if you are not specific enough why it is relevant, or if you think one more step, you'll figure out that is helping everything, not just the reading, right? So if I ask you the question like this, very specific, right? It's not addressing this, right? It's not proposed to address this specifically. Agree? Okay, yes.
What does the story here exactly mean?
So it means like, okay, I have done something that's specifically optimized for reading strings of data. So for example, right, strings of data, so you want strings of data to be allocated together, that would help, do you agree? So that's why large chunks is considered as a factor of contributing to this one. Right. But a flat structure actually make the lookup of everything faster by not going through the hierarchy. Right? So that's not it. Right? Same thing, right? Do you think the fourth one will apply? Not really, right? How about the fifth one? Yeah, right. So if you read the paper carefully, right, is that so traditionally, right? Traditionally, if you are accessing a file, highly likely you may alter the metadata of the directory, right? And if there are multiple clients trying to access the same directory, what happens? Race condition, so you don't want race condition. So how do you address the race condition? Lock, you can only do lock. And the thing is that if you have a hierarchical design, the whole directory path has to be locked, right? And typically, for example, we love to store a lot of things in the same directory, right? Like home, that's a popular directory. So which means that if somebody is trying to access home, no one else can alter the content of home, right? Can you imagine the performance in concurrent operation under that? Right, that's not going to be good. So actually a flat structure is really good for supporting concurrent operations because all you need to do is to lock that specific table entry that's related to the file that you are accessing, then all set. And others sharing the same directory can still work on other files without having problems. So this one is actually a good one to support concurrent operations. So how about the last one? Bandwidth is more critical than latency. Why not? So it helps the latency, right? And so here's the thing, right? Some of you might have the argument, yeah, it helps to improve the bandwidth. Yes, it does improve the bandwidth. I will show you later. But it also improves the latency, as you can tell, right? Because when I want to retrieve a file, I don't have to go through so many items. So it actually improves both. So you cannot say this fulfills bandwidth is more critical than latency because it actually makes both bandwidth and latency better. It's a design making both better, right? So the only thing that fits the flat structure would target to address for the demand of the workload in data center is actually a design for supporting concurrent accesses. However, it does help address the last one in a way that it not improve the bandwidth, but also help the latency. So here's what I can tell you, right? Remember, this is what you have to do in MFS. That you want to open a file, you have to go through the hierarchy. However, now with the flat structure, remember, all you need to do is consider this thing as a full pass. You just consider the full pass as the entry that you want to look at in the mapping table. And the mapping table is like a hash table, right? So what happens is that you use the whole string as the input. And the Google file system would just give you the locations of the file that you're looking for. All set. One round trip, all set, right? But previously you have to have 6 round trips, right? But now only one trip, round trip, right? So the latency is a lot shorter. And the other thing is that on the network side, because you waste fewer bandwidth in the lookup, so your bandwidth also get improved. This is a very, very, very neat design. Right? I hope our file systems are designed like this, right? So you only need this in Google File System, right? So now, my question would be, now you know the Google File System has a spatial structure, a master server, a client server, a chunk server. So can you tell me how many of the following statements are true about their design? So some of you were asking on the chat saying that, will large files lead to fewer entries in a lookup table? Yes, but that doesn't affect the fact of the file system design when you talk about the flat structure and the Google File System structure, because this is just about how many files in total you need, right? And in fact, if you think about the algorithm that you learned in lookup tables, it's typically just a hash table. So it's order, if it's a hash table, the order is 1. It's unrelated to the number of entries you have in the table. Hopefully that would address your question. All right, other than that, it's time to wrap up. 10 seconds. 5, 4, 3, 2, 1, time is up. Okay, so now looking at what you guys say. Okay, so this time you notice almost a lot of every of you think the answer is C. So can I have some of you telling me why do you think is C? So for people here, what do you guys think about the first statement? is the cluster only have one single active server for storing the metadata? Yeah, right, single point. Okay, so that's what I said, single failure point, and when one died, they will pull out the shadow master as soon as they could. Sounds great. The chunk server in Google File System may contain data that can also be found on another chunk server. Yes or no? Yes, right? That's what they call by replica. And in fact, right, by default, every piece of bit of your data, you will find 3 replicas at least in Google File System. Right? Replica, replica, replica. Right? Everything is duplicated for 3 times. Right? It's really important. So 3 times. All right. The chunk server is dedicated for data storage and may not be used for other purpose. Yes or no? For this one, what do you guys think? Does Google guarantee that the chunk server is only used for data storage? Yes? No? Okay. Remember, what's the mission of Google? Don't go evil. Making money, right? So here's the thing. Do you think this third statement is good for making money? No, so it's not. Right? And the answer is that, right, if you check the paper, right, it's easy to run both a chunk server and a client on the same machine. And by client, it means the client of accessing Google File System. And as long as machine resource is permitted and lower reliability caused by running possibly flaky application code is acceptable. Right? So it's possible that they have a machine that is dedicated for storage, well, that has the data storage with large hard disk drive. However, remember that, right? If because those data access time could be long, right? So when you are accessing data, your processors are probably idle most of the time, right? So their idea is that, well, if there is a server dedicated for data storage, it's highly possible that that server is underutilizing their computing resources. So why don't we just use them both, right? By providing this multi-tenancy in a way that you can have your computation also on the data node. And in some sense, right? If you're running MapReduce, saying that the mapper on this server, and if you're lucky enough that the data is just happen to be on the same machine, it also helps the performance, right? So this design not only save the money, well, although the main purpose is saving the money, but also make the performance potentially better, right? Can the client cache file to improve the performance? No, right? So surprisingly, no, right? Neither the client nor the chunk server cache file data, right? So this is a very counterintuitive design in Google File System that we try to leverage caching as much as possible in most of our file systems. However, that's not part of the Google File System, and they have a reason for that, right? Because remember, right, when we talk about consistency, when we talk about coherency, you guys know that, well, if you have to maintain that, it will make the whole design complicated and your file system may not be able to maintain the stateless thing, right? And Google wants to make things easier. Again, right, if you make things easier to maintain, save money as well, right? So it's all about money, right? So simplify the design. So 2 of them are correct, the first 2. And the first 2 are very important, especially the second one, you have replicas, 3 replicas, replica. Really important 3 times, right? Okay, so here is the Google File System architecture. So it has a single master, whenever your application wants a file, this is what happened, right? You tell the Google File System client, you can consider this is a local file system mounted on the machine that runs the application. So it still receives the conventional C programming language convention that the file name size. However, remember here, the file name is the full path, right? And once the client receives the full path, instead of break down the full path into directories like NFS, it just sends the whole full path to the master. And on the master side, it's just a virtual hierarchical file structure. So this one is virtual, is an illusion. It's actually a mapping table, a hash table that potentially on the back end also made by big table. And you just perform one lookup, and the lookup table would throw the chunk locations. Here I say chunk locations, which means, remember, each piece of data has 3 replicas. So here I say chunk locations, which means that the server would give the client 3 different locations to access. And the master server in the meantime, it also checks the status of these replicas and the machine to see if they are still alive, right? So they return those chunk locations that are still valid to the client. And it's up to the client to pick one of the chunk they want to access. So this is the design of Google File System. When you are reading data. And when you are, so in this way, right, 2 things could be achieved. First of all, we have replicas, right? So if I try to get chunk from one server, it failed or not returned within the timeout, I can immediately, on the client side, I can immediately pull the data from others. So the replica helps to address the reliability issue if the hard disk drive failed or the hardware itself failed. Or think about that, right? The client can randomly pick data from one out of the 3 replicas. So if the randomness is good enough, we can automatically achieve load balancing, right? So here is a thing, right? And the other thing that you can see is that some of you might be questioning, oh, I only have a single server, right? Wouldn't that server be super busy? So the answer from the paper is that, well, thinking about that, right? You only need a single server for lookup. And we already made the lookup a lot simpler than it was for other file systems in a way that it's just a single table lookup. So it's not going to take a lot of overhead, right? And remember, what's the purpose of Google? Making money, right? So if you want to design a system with many replication of the master server, it's costing more money, right? So that's not an economical design in terms of their perspective, right? So their argument is that, well, the control path access is not on a critical path and is not that heavy traffic. So why don't we just have one single server and it's good enough, right? And that design, the decoupled data path and the control path actually make that is offload the master server because your data doesn't move through the master server. So the master server doesn't have to be multiple. You don't have to think about the load balancing about the master server. It's all good, all right? So, and their argument is here, right? Like, so it won't become a bottleneck because the way how we do it, right? So the distributed architecture looks like this. They have a single master server, they have a child server, they have the client, which I already explained. So reading data from GFS is like this, right? So you want to, and I think I just mentioned that, right? I just take one chunk. So what happened on writes is like this. Writes are more complicated in a certain way. First, I want to write data
And again, Google File System will try to get the chunk index, and the master server will tell the client, okay, here are the locations that you must update. You must update. So then it becomes the client's responsibility to check the data is first updated on the primary chunk server. And one thing that is different is that, well, because the client wants to be off the hook as soon as possible, so client also send data to other chunk servers, and it's done. Right? The replication is done in this way. It's the client sending data to the locations that the master server asks the client to do. Right? So you thought the replication is done automatically within the Google File System. The answer is no. It's actually the client helps the Google File System achieve the replication. So it's not the job of the master. So that's why you only need a single master, because the responsibility of a master is really light. You just tell the client, here are the things that you need to do, right? And the write command is issued on to the primary chunk server. However, those chunk servers, they will coordinate with each other to make sure that the data sent from the client is finished and presented on each of the chunk server and finally return the state to the master server. So that's the whole idea of Google File System design in terms of updating data. So as you can see, right, there might be cases that when I finish writing this part are not ready, this part are not ready, right? So what if somebody wants to read it, right? And if you look at the protocol, whenever I'm done with the primary server writing, the client is ready for the application to go, right? So others can continue execution as well, right? So it's really an issue that the consistency thing that a lot of you were worried about, right, is indeed an issue in Google File System. And this is Google's response. I don't care. Being honest, that's my take on this, right? So here's what they do, right? So they say we use a relaxed consistency model, right? When you hear the word relax, right? Relax, right? Be chill, relax, right? You know that they are not going to deal with it seriously. Otherwise, they won't use the word relax, right? So this is what happened, right? So they say, well, we have a few states associated with your data. So if you have a file, so they have different types of access, right? So if you have okay, first of all, right? If it fails, it means that, well, nothing here is trustworthy, right? And if your file is code-defined, which your file is now in a status of defined, it means that, okay, the content is trustworthy, and there may be some inconsistency, but mostly trustworthy. And there is also a state called consistent but undefined, which means that the data is mostly trustworthy, but be careful, it's not finished yet, right? So that's the status that your data is now in the progress of updating, however, it's not done yet. So they have this kind of consistency status. They will tell the user, here is where your data are, the status of your data. And see the last sentence? Is up to you, up to your application to decide what do you want to do, right? So here is their relaxed consistency model. They simply tell you what's the progress of update of your data. However, I tried to do nothing to make sure it's consistent. Can you hear that? I only tell you if your data is consistent or not. How to handle the inconsistency is up to you. And my protocol doesn't guarantee that your data will be consistent. If it's inconsistent, you deal with it. That's the philosophy of Google File System. So it does nothing to make sure that your data to be consistent. That's the conclusion. All right, so a lot of you will think about, oh, Google is the best company all over the world, and they must guarantee that my data is safe all the time. No, they did nothing about that. Well, at least in this version of the Google File System. So this is one of the interesting papers, right? So sometimes people will say, well, why am I reading paper? But actually, a lot of industry research labs or even the companies, and actually, we are going to read more and more papers from companies these days. Like today, you read papers from Google, Microsoft, next lecture, Facebook, and then we are going to read paper from VMware, right? So it's highly relevant, right? So some of you think, well, if I work in industry, I never care about research papers. That's not true, right? Because actually, right now, the in terms of writing papers, industry is taking the lead in some sense. And if you read these papers, they actually point out a lot of valuable things that other places that you won't find. So if you want to read in section 7, they say, well, there are Linux drivers issues rendering the hard disk drive status inconvincing, right? So a lot of cases we design file system relying on this performance counters that's reported by the hard disk drive. That's not reliable. And another thing, right? Well, we say about the synchronization, right? And in file system there is an operation called fsync, which makes sure that I have finished the write. I have to finish the write before I can proceed. And they say in the conventional Linux system design, the time of file sync is actually in proportion to the total file size rather than simply the portion that you want to update. So they fix that bug. And the other thing is that the mmap function originally they only have the single reader write lock. So there's only one in a system can perform mmap operation, which is somewhat reasonable in some sense. If you have only single, if it's a multi-threaded model, and if you have only single pool of memory, but they kind of like fix that, and they contribute. They say, well, due to thanks to the open source community, so we can fix it and contribute to the rest of the community. That's what they said in the paper, but in reality, they never did that. In reality, they never did that, right? So that's the thing about Google, right? And after reading this paper, after knowing the reality, I start to Google this company differently in a way that, well, originally everyone is advocated that this is a company, don't do evil, do the right thing, but they're just not too different from other companies, right? It's never open source. The Google file system is never open source. The Google file system is never open source. And another thing that a lot of you might be questioning about is that the single master design. So Google file system saying that this will not be a bottleneck. The metadata operations decoupled, and clients can cache the metadata. But what if the master server fails, right? And actually, right, the thing is that the Google file system, the paper was published in 2003, and that was actually the time that Google was still a company with a lot of dreams. But later on, they did update the Google file system design a lot, but they never talk about the design in detail because now everything in Google is a secret and they don't want to share with the rest of the world because they are afraid that other companies will catch them up. So they briefly mentioned in an OSDI 2012 paper right? They say, well, they have a file system called Colossus as the successor to the Google file system. And regarding the single master issue, they have a very brief discussion with an ACM editor in an interview. So if you're interested, there is a paper there is an interview in ACM2, a magazine published by ACM, and they say they have a case study on the status of the Google file system at that time. What they said, they say, well, the Google file system, right? The paper first claim is not going to be a bottleneck, but if you read their interview carefully, 10 years later, they finally agree. This proved to be a bottleneck. Right? This proved to be a bottleneck. But I would say time changes, right? Because when the time Google file system was rolled out, Google was still a small company, not too many services. However, later on, when Google tried to grow, the service scales up. Single master design doesn't work out, right? So it turns out that now they are more like other systems that has multiple master servers as well, right? And the other thing, right? Originally they say their data centers are designed for large file accesses. That was true until they have the very popular service, which even UCR is leveraging today, the Gmail. Right? How big is your email? Right? These days, people just use email as text messages, right? So the email can be really, really small, right? So actually, right, what they talk about is that, well, now, right, the average file size that they have is getting down to 1 megabyte rather than their original design of 64 megabytes. So they have to deal with it somehow, right? So what have you been doing? Design Google GFS to work with 1 megabyte. We haven't been doing anything with that design, and distributed master server will provide is essentially a whole new design. So the thing is that it sounds like they are going to have a different file system design for Gmail service instead of leveraging the Gmail, the original Google file system. But it's indeed a different file system that they would need to address that, right? So that's something that's interesting, and but one thing said is that from then on, Google never talked about their design. However, the following two papers, the Microsoft paper and the Facebook paper, actually can tell us if you want to design a file system in a network for small files, if you want to design a file system with multiple masters, how that would look like. So that's why we have the other two papers in line that we are going to read. But this is actually one of the papers I like, in a way that you can see lots of interesting topics, like how they deal with the namespace locking, how do they place the replica, how do you re-replication if one server fails, how do you make sure that the replication is balanced well among servers, and how do you do garbage collection, how do you make sure your data integrity, how do you know your system failed, and how do you discover that? Right? So those are interesting topics that I would encourage you to go through in a paper. So this is actually one of the best papers I like among the whole quarter of the list of the paper that we have read so far. But let's wrap up on this paper a little bit, right? Today I'll check there you go. So first of all, right, with replication, distributed storage, this is how they address the fact that those disks are failed frequently, right? You just need to have more copies and you are done, right? Cheap disks, they are cheap. However, if you want to buy expensive disks to support that, that's not going to be cost effective. And the whole company is trying to save money. And large files, in contrast to small files for personal data, right? That's
that's addressed by large file chunk size. Reading streams of data, sequential append, large file chunk size. Flat structure address the concurrency. Bandwidth is more critical than latency. That's also by large file chunk size. So hopefully this summary will give you an overview of how does what address the why of the design behind the Google file system design philosophy and agenda, right? So that's actually one example of things that I want you to learn in the operating system class is that when you propose a what in your system, make sure that you have a why behind it, right? And this table, this example of the Google file system design is a good example, good template on that. All right, so, but is the Google file system the best file system? Apparently not, right? It only supports a very relaxed, consistent model. Scalability, the single master, as we mentioned, that was an issue. Even Google itself agreed that's an issue, right? And it's only efficient in dealing with large data, right? And even the editor asked the question, they can only say, yeah, it doesn't work out, right? So we need a different one, right? The other thing is that there's nothing mentioned about the geo redundancy, right? So let's talk about, and some of you might think about why geo redundancy is so important, right? And some of you think about, right, United States is the greatest country all over the world, right? So we don't need data centers everywhere else, right? However, right, think about the Golden State, California, we love it, we consider it as home, but this is actually a story happened during my years as a PhD in UC San Diego, is that I have been suffering from 2 nights without electricity because just one stupid strong wind blow and knocked down one of the power cables in one of the desert in Arizona, and the whole city gets blackout for 2 days. And sometimes, right, special events like in 2013, Beyonce was the halftime show for Super Bowl, and probably because Beyonce is so hot, so it actually overheat the power supply of the whole stadium. So it turns out the stadium was blacked out for half an hour, right? And the other thing, right, Beyonce caused the Super Bowl blackout. It was a hilarious title, right? And the other thing is like, okay, wildfires, right? You remember that probably last year, right? And so there are so many things that can cause the, and we are now living in a world with a lot of dynamics, right? So you cannot rely on a single data center. So we definitely want to have a design that allow your data centers to be across the whole nation or the everywhere on Earth, right? So since Google doesn't say a lot about their design, let's look at the other company, and that will give you very good proximity about the design of this kind of file systems. So this paper is coming from Microsoft. So so here's the thing, right? Microsoft, they are by no means the most innovative company in the world in terms of their service or products. However, a good thing about being in that position is that let's wait and see what other people are doing, and they try to catch up with a better design. So that's the philosophy of Microsoft for a long time, right? So, and Microsoft is also a different company from Google in a certain way, is that their workloads are pretty different. So if you read this paper carefully, that was the workload that Microsoft was trying to address in their data center. So different from Google in a way that Microsoft is also a company that owns a big game and entertainment division, right? If you are an intensive gamer, you probably noticed that Microsoft just acquired Blizzard, right? Which probably like wastes you a lot of time when you were an undergrad, right? Same here, right? I used to play a lot of like Diablo or I don't want to tell you which generation it is, but
Diablo, some generation of Diablo, some generation of Warcraft, right? Some generation of StarCraft, right? So it's also part of Microsoft now, right? So Microsoft has a big division of entertainment, and most of you don't know what is this, but thinking about this is like an iTunes store, right? So, and how big is your music? It's probably like a few megabytes, right? How big is your gaming data? A few kilobytes, a few megabytes, but also have a lot of other data that might be large. But in reality is that Microsoft's data center is different from Google's data center in the very beginning of their design in a way that it's a data center that has multiple different types of a workload that they have to address, right? So it's actually so they are trying to roll out a single cloud platform that powers this variety of services in Microsoft. So they have three main types of data. So one is blob, and those are typical binary data that includes pictures, Excel files, right? Remember, Office is also a big division of Microsoft. And HTML files, virtual hard disk drives, big tables, database backup, pretty much everything, binary data. But they can be various in size. Table, database table, right? Remember, Microsoft has an Access, which is a big part of their service. And they also have, because you have the service like Hotmail, because you have the service of Xbox, so they do have to store small messages, like the user email, like the game log, your shitty chat log when you are gaming with others, right? Those are messages that are small, right? So this is very different from Google, right? Google is all about big files. However, Microsoft not only have big files, they have a variety of different files. And even those files, they are different, right? So here it is, and the other thing, right? The other thing, what I think is that Microsoft is also different from Google in a certain way that in the very beginning, Google is just a small company. So their main customer is actually themselves, their services, right? Like Google File System is targeting at their own machine learning perspective, data mining perspective, Google Earth, Google Maps, Google Search, right? Everything with a Google on it, right? But at that time, Microsoft is already a company that serves the backbone of other companies. So it turns out that they have to listen to what our customer wants. And their customer says that we don't want to hire engineers to deal with a consistency issue. Okay, let me give you, so sometimes, right, engineers hate PM because those people, they go to the customer and whatever customer wants, they would agree, right? Like strong consistency. It's very difficult to maintain. If I'm an engineer, I would definitely say no to have this feature in my file system. But there's one thing, I bet that's what the customer wants. The customer wants strong consistency. Sure, we can do that. We are Microsoft, no problem at all, right? Even Google cannot do it, right? So first of all, strong consistency. The other thing, right? Another thing, right? Google didn't address very well is that when company scales up, right? You have to make sure that your design can scale as well. However, Google were not a big company when they designed the Google File System. So later on, as you can see from the interview that I cited, they do suffer the scalability issue with their one active master server, right? And they do not accommodate the small files in the original design because they never thought about it, right? Now, in Windows Azure design, because they already noticed that we are a big company, we have many customers, so a scalable namespace storage is definitely one something, right? And our customers doesn't want the service to be going down anytime, anyway. So disaster recovery, even though the nuclear weapon launch, right, the service still have to go on, right? Not sure which PM agrees with that, right? But that's part of the feature. And finally, well, Microsoft is still a company that needs to make money.
Right, so multi-tenancy and the cost of storage is still something matters to them. So this is their design. And as we mentioned before, right? Well, as an engineer perspective, if you really don't know how to deal with the problem, try to add another layer. So let's see what layer Microsoft tried to add on top of Google File System design to address the issues. So this is what Windows Azure proposes. So if you look at this, right? Okay, first of all, the design is like this. So it has application, it has client. So this part is pretty similar to Google File System. And then it has a domain and service. And as you know, in your in internet protocol, the domain and service can be many, right? And this domain and services, or say this domain and server, is considered as the functionality of the master server in a certain way that give you the lookup result of where in the world can you find the data. And then there is location services. Now, if you look at the design, they have a few the storage stamp. And if you just look at the design of a single storage stamp, you will figure out its base is a granularity of storage provision for domain geo-replication. And a storage stamp is essentially 10 to 20 racks with 18 disk heavy storage node per rack. And another thing is that if you still don't get a feeling about what a storage stamp is, a storage stamp is essentially a Google file system. So what does that mean? Is that on top of a Google file system, we add this, we add this, we add this. Right? That's how Microsoft achieved their goal. Right? So why am I saying the storage stamp is essentially a Google file system? But before we talk about that, let's look at the whole process. So another thing which Microsoft changes is, well, Microsoft is a different company. So is that instead of using the full path and file name as a way of looking up, they use URI or say URL as an identifier of data in Windows Azure storage. So when you want to open a file, this is what they do. You have to use https account name.service.core.windows.net partition name object name to access that particular pieces of data you want. So Windows Azure design totally abandoned the path name and file name abstraction. Everything is now considered as an URI, so it's essentially a web location, right? And with that, right, when you type that, the client will consider, well, because this is like a web address, right? So you can use the domain and service to figure out which server that I can look out for my data. And then based on the account name, the location service would figure out where the user is and what are the set of the best servers that I should respond. Then it can return the virtual IP of the stamp. Of course, the virtual IP is within the Microsoft network VPN or something, right? And then the client can use the virtual IP of the stamp. Remember, the stamp here is a Google file system, right? Or you can consider it as a data center, as a Google file system in the data center, right? So use that IP, the client connect to that one, give the partition name and the object name. So this part is kind of like similar to Google file system because the partition name can be considered as the path name, the object name can be considered as the file name. And use that part. It goes through the Google file system or say the storage stamp and return the data directly to the client. So on a high level idea, it has some flavors of Google file system already. Now within a stamp, what it looks like, right? And
So this is what a stem looks like. So again, right, the left-hand side is the Google file system. Remember the master, the chunk server, and there are replicas. So in Windows Azure, the storage stem, they have a front end, they have the partition layer. You can ignore those for now. But within a stream layer, it's pretty similar to the Google file system in a certain way, which I want you to answer this question to see how are they different, how are they the same. All right, let's wrap up in 10 seconds. 5, 4, 3, 2, 1. Time is up. Okay, look at what do you guys think? Okay, C is the most popular answer, so I will skip the discussion for now. What do you guys think? So comparing, so the stream server, we say the stream servers, they are considered, they are essentially the chunk servers in Google file system. So, but why are we calling them stream? And how the stream is different from Google file system? So, first statement, is that correct? Sorry. For the first statement, is that correct? Yes, right. A stream is a list of extents, which an extent is consists of consecutive blocks. So, regarding the definition of extent, is it the first time you see it in a class? Is it the first time you see it? When is the first time you see it? Extent file system. Regarding the definition of extent, is it different from the extent that we learned from there? No, right? So here's one thing, right? The extent here is the same as the extent in extent file system. It consists of consecutive blocks. So in Windows Azure, right, they define a stream as a list of extents. So you can consider the stream is actually a collection of pieces of an object, right? And mostly because they are extents, so they are consecutive. So they also have the flavor. And remember, right, extent file system works well for personal computers, right? So you can somehow saying that, well, this kind of design will work for small files as well, right? And because it also has the consecutive block nature. So it works for large files as well, right? So using stream as the unit of storage is actually fulfill the agenda that they have various size of files instead of fixed size chunks that are always large as in Google file system. How about the second? Do they have the checksum? Yes, right? So this is the string, right? So a string is actually the basic unit of storing object, and for the string is actually a collection of extent, and extent is actually consecutive blocks. And each extent also have a checksum because this is Microsoft. We want to make sure that our customers' data are safe here, so they do have checksum. How about the third statement? Append only? Yes, right? Append only, copy on write. Have you heard that somewhere? append only, copy and write, all of that. What file system? Log structure file system, right? So, hey, is everything connected now, right? You learn all of those and they are there for a reason, right? So with that, you know, well, it is append only and the end of the string, right? Copy and write. So this design is optimized for writes, right? So now you know the string server design also accommodate writes, which is different from Google File System in a way that it's only good for large writes, right? Now, the fourth thing, two strings can share the same set of extents. True or false? So if you read the paper carefully, right, it's actually true, right? And why is that? So in many cases, right? Okay, so here, this is how you use your computer, right? If there's anything you can copy, you will copy. If there's anything you can copy paste, you will copy paste, right? So this is how you start your homework. Typically, you have a Word file from the last assignment. Control C, copy it, Control V, paste it. Right, so in the very beginning, when you create a new file, very likely it's going to leverage a lot of content that you already exist, right? So if you have this neat design, right, I allow two strings to share the same extent together. When you create a new file, first of all, you don't have to copy the data byte by byte in your storage. The other thing is what? It saves space. Right? Because you don't actually need to create space for the new file. In some sense, you also save the money you spend on the hard disk drive. Right? So this is a very neat design. And another thing, which they didn't mention in the paper, but I do think is essential for every cloud storage that could potentially be used to store multimedia data. So a lot of us would favor the same set of music, right? So if you store your video clips or music files in the cloud, you will definitely find a lot of duplications, right? So as a user, as a company who also provide like an iTunes-like service, if people download a file from my service, I immediately know that some other also has the file. So all I need to do is to create a link in a user profile saying that this data is linked to this extent without actually create a copy of the music in a user's repository, right? So again, saves money. So everything here is true about the string, right? It helps to duplicate and save this space, save money. So this is a very neat design. And actually everything here about the string is correct. And another thing that is interesting is about the string, they have the feature of sealed. And we can talk about that a little bit later, but let's wrap up in this way. So now we know there are strings, and I try to convince you that the string server is like a Google file system. So let's look at this. In Google file system, they have the chunk server, but in the string layer, they do have extend node. And within the extend node, when you create an extend, you will receive the extend content from the upper layers, and the function of upper layers we will discuss in the next lecture. But once you receive an extend, which is part of your data, the string manager, which you see there are several string managers, right? So it's actually like a Google file system, the master server in Google file system in a certain way that is managing where should I store the extend. And the string manager, they would decide
which extend node, where an extend node, you can consider that as a chunk server and should store the incoming extend as well as creating replicas on that. So again, this Windows Azure design also has 3 replicas of each extend, right? 3 is the magic number. Everything important, you should repeat it for 3 times, right? So they have the primary, 2 secondary for each extend, 3 copies of data. And isn't that similar to Google File System, right? So are you convinced that the stream layer is essentially a small Google File System now, right? So whenever you write, similarly, right, your partition layer directly write to the extend node, and the replication is done within this extend node. So this is also similar to Google File System, right? And once the primary server is done, act to the upper layer, so your application can resume sooner. So this is also similar to the Google File System, right? So essentially, inside the stream layer, everything is pretty much similar to the Google File System, except they have the concept of a stream, which is an enhanced version of chunks in Google File System in a certain way that, first of all, chunks are fixed size, but we use extend, which is variable size. And we have checksums, so the data is safer. We allow the reuse of extend to save the cost, right? So those are the enhancements of Windows Azure's design over the Google File System. And the thing is, right, one thing that Google File System doesn't do is the replication over the Google File System level. So so in Windows Azure storage, the stand itself is considered as a Google File System. And they have the partition layer on top of the Google File System to coordinate the inter-stand replication. So it means that your data not only exists with 3 replicas in the stream layer, I also create a clone somewhere else in the data center. And the data center can be either somewhere else. So it's also providing some sort of geo-replication of your data and the whole file system service. So that's the whole idea of the Windows Azure design. All right, so we will wrap up with Windows Azure design in the next lecture. But before you leave the classroom, I know you must be aware that the project due this Thursday. And remember, please submit your project, no matter it's dead or alive. Because we will have a revision period for you, and make sure that you fix the bug before March 11th. However, you need to make an appointment with our TA to make that happen. Our very last reading quiz due next Tuesday. So that's the last chance. And one thing, we do value your opinion about this class. So if you would like to, please submit your email by March 11th as well. And if you do that, make sure that you take the screenshot. You will receive a full credit reading quiz. So give you for free, right? Finally, some of you asked about the final. The final will contain 2 parts. Part 1, time limited. Part 2, unlimited. So check the details on Piazza. I have mentioned that. Other than that, enjoy the rest of the day. I will see you this Thursday.
Professor, I had a doubt.
Sure. What was that?
You said the 2 sets of comprehensive exam questions, right? So could you give an indication how those questions would be like?
No.
Okay. Would we have sub questions or something?
Well, I mean, the thing is that, right, one of the important bits about the operating system that should be covered by these 2 sets of questions.
Okay. Okay.
Right?
Okay. Thank you, sir.